Okay, everyone, thanks for joining. This is Matt Schultz with the Sustainable Phosphorus Alliance, and you're here for the Sustainable Phosphorus webinar series. Our topic today is phosphorus recovery from water resource recovery facilities. And we have a great set of speakers that are going to be presenting today. Just by way of setting up the topic, we've practiced circular economic thinking while dealing with human waste for a long time, thousands of years, at least in the West, dating back to ancient Athens, where sewage was used as a fertilizer. In a truly circular economy, of course, there is no waste. Waste is what happens when, instead of closing the loop on consumption by recycling materials, we send those materials to landfills or burn them or release them to the environment in some uncontrolled fashion. In the US, we do waste perhaps 45% of the materials in our own waste, and these materials have proven agronomic benefits. Included in these are carbon, which builds soil structure and feeds soil microbes, plant nutrients such as nitrogen, and of course phosphorus, which is our main concern. We need to be ever vigilant about implementing processes that remove harmful substances and pathogens before applying these recycled nutrients to farms sustainably. But the model of plant feeds animal, animal feeds plant is about as ancient and circular as any. Today's speakers, to their credit, have all developed and implemented technologies that help recircularize our food system by recycling nutrients, and some of these technologies even extract phosphorus specifically for reuse. And so before we get into the webinar itself and I introduce the speakers, I want to introduce Karen Culver, who's our marketing and development manager, so she can tell you a little bit about the Sustainable Phosphorus Alliance. Karen, do you want to take it away?
Absolutely. Good morning, everyone. The Sustainable Phosphorus Alliance is a members organization, and we serve as North America's central forum and advocate for the sustainable use, recovery, and recycling of phosphorus in the food system. So we are a members organization. If you look to the right of the slide, you will see the logos representing our founding and current members and strategic partners. They are the organizations that are involved with our alliance today. What we do? Well, we facilitate networking among many diverse players from across the phosphorus value chain via knowledge sharing events. So those include our annual conference on phosphorus sustainability, and we are currently planning our next phosphorus forum for early next year. We also have technical webinars like the one that we are having today on phosphorus sustainability, and have our quarterly newsletter, blog, and social media accounts, which we use to share subject matter on phosphorus sustainability. So please follow us or connect with us there. We also orchestrate working groups, and currently we have a biosolids and manure task force, and that is in process, and we will have a field to watershed phosphorus modeling workshop coming in August. We provide technical input on metrics development and research prioritization for other organizations, and also represent the North American phosphorus sustainability community with other organizations and within the global collective. And we offer a branding opportunity to organizations working in this vanguard. So we offer that branding opportunity to you as well. If your organization is not currently a member, we would really welcome talking to you about joining us and getting involved. We do have a community resource on our YouTube account. As you can see, we have 10 hours of video footage of phosphorus sustainability discussions, which are there for you to view and to watch. And this presentation will also be on that channel. So, thanks, Matt.
Great, thank you, Karen. And our agenda for today, we've just gone through the introduction. We're going to have 4 presentations. They're each going to be about 15 minutes, and they're going to be in the order outlined here. First Lystek, then Renewable Nutrients, then Ostara, and then CLEARAS Water. After that, we'll have our question and audience session with the audience, and you can submit your questions via chat to me, and we'll display those up on the screen for the panelists to answer at the end of the chat, and then we'll wrap it up after that. Here's some photos of our speakers. These are the 4 speakers for today, and we're going to start with Mike Dougherty, who's the Director of Product Management at Lystek International. He also is joined by a colleague who I'll let him introduce. A little background on Mike, a little bio. He is a professional agrologist with experience managing beneficial use of biosolids projects in British Columbia, Alberta, and Ontario. He holds a Master's of Science in Environmental Biology from the University of Health, and is a member of the Ontario Institute of Agrologists, Canadian Society of Soil Science, and Grey County Soil and Crop Improvement Association. Prior to his role as Director of Product Management, he was the Manager of Fertilizer Production and Distribution at the Southgate Organic Material Recovery Center, and he's responsible for fertilizer sales and coordination for all of Lystek's sites, as well as the development of alternative product initiatives. And Mike, thank you for joining us. I'll pass it over to you.
Okay, thanks a lot, Matt, for that introduction. I'm Mike Dougherty, Director of Product Management for Lystek, and I'm going to talk about our company and our approach in managing our end product, Lystegro, which is about biosolids-derived fertilizer. So our company, we're a biosolids and organic management and processing company. We're developed at the University of Waterloo in Ontario, Canada in the year 2000. The technology is a thermal alkali hydrolysis process, which produces a Class A EQ biosolids in the United States and a Canadian Food Inspection Agency registered fertilizer in Canada. The process itself is thermochemical hydrolysis. We use three things: temperature, pH adjustment, and shearing. So we heat the material up to about 170 degrees Fahrenheit or 70 degrees Celsius. This is with low pressure steam. We adjust the pH to approximately 9.5 using different alkali sources. So that can be lime, cement kiln dust, potassium hydroxide, or any alkali source really, depending on the size of the deployment and what's available in that area. So normally we adjust the pH to 9.5, but that is flexible depending on different regulations. So we can adjust it to all the way up to 12 if we want. And that's going to be dictated by the regulation in those specific areas. The third aspect of the process is high-speed shearing. So think of the process happening in a large reactor. Within the reactor, there's a blade spinning at approximately 1,000 RPM. That blade is causing cell lysis. So that's where the Lystek name comes from, lysis Lystek. And so those three things, the heat, the alkali addition, and the high-speed shearing, that is the Lystek process, and that's causing hydrolysis. And what we end up with is a product of approximately 15% solids in a liquid form. Normally, 15% biosolids would not flow. It would be in a cake form, but because it's gone through our hydrolysis process, it is a high solids liquid material. We have two types of deployments. One is on-site processing, where we can retrofit our system into an existing wastewater treatment plant. We have 4 current deployments and 3 more under construction currently. The existing deployments are in Elora, Guelph, and St. Mary's. Those are in Ontario, Canada. Another one in North Battleford, Saskatchewan. 2 more under construction in Ontario, St. Thomas and Innisfil, and another one in St. Cloud, Minnesota. These deployments can range in size. We can have reactors of 5 cubic meters to 9 cubic meters in size. The Elora site, for example, treats the wastewater from a town of 3,000 people. Guelph is 100,000 people, but there's no reason it couldn't be a much larger deployment. We also have off-site processing facilities. These are Lystek-owned facilities where we bring in materials from several locations, process on-site, and process into in Canada, fertilizer, and in the US, a Class AEQ biosolid. In Canada, we have the Southgate, Ontario facility, the Iroquois, Ontario facility, and then the Fairfield, California facility. Fairfield's located about an hour north of San Francisco. The Southgate and Fairfield facilities, both plants are able to process 150,000 tons in a year. A little bit about the biofertilizer. It's a homogeneous liquid with high solids, approximately 15%. Has a relatively low viscosity for something with such a high solids content, approximately 5,000 centipoi. This is something that our pumps can handle, and it's, more importantly, it's something that the liquid application equipment can handle. It's fully pumpable with using the traditional liquid application equipment. In Canada, it's a Canadian Food Inspection Agency registered fertilizer. In the United States, it's a Class AEQ biosolid. The material is pathogen-free. It also has long-term storage stability. So this means that there's no pathogen regrowth while in storage, and the material does not settle out. The solids remain in suspension. In terms of product management and managing a biosolids-based biofertilizer, there are inherent challenges. Those challenges mainly are changing the perspectives on something that has traditionally been considered as a waste. This material has traditionally been given away or sent to landfill in many cases. What we're trying to do is look at it as something of value, use it as a fertilizer, and charge for it. And the way we've done this is focusing on positive messaging. We're providing a product and a service to our customers, which are the farmers, and we prove that it works. We use third-party trials through independent researchers to verify that it works. This is just an example of our best management practices. So even though in Canada we're a fertilizer, in the US we're a Class AEQ biosolid, which has much less regulations than a Class B material, for example, we still use best management practices, common sense really. This is just an example of a document we use in Ontario, Canada, what our application contractors use and what we dictate that they use. So setbacks from waterways, depth of groundwater, different things like that. And that's just to ensure that the product is used as appropriately as possible. Best management practices also include looking at it from an agronomic standpoint rather than maximum loading standpoint. So we apply based on agronomics, soil samples, cropping systems, and what the farmer is looking for, not based on the maximum amount that we can apply per acre. We also require payment. So we've sold every single drop of product that we've produced. We've been able to charge more and more for it each subsequent year as people see that it works. Another aspect of getting payment for the material is that the farmers are only going to use as much as they need. If they get it for free, their mindset is that they'll take as much as they can get. But if they have to pay for it, they're going to value it, and they're only going to use as much as they actually need. This is just a depiction of what the application looks like. There's an application on the left-hand side. You can see that the material's been applied, and on the right, it's just what a typical application rig looks like. Basically, what's happening is there's a slit being opened up. The material's being put into that slit, and then there's closers coming behind, closing it over. Another important aspect of our programs is that we know exactly how much has been applied and that it's been applied evenly. To do this, we utilize we utilize agricultural technology. This technology is improving and increasing all the time. So all of the applicators have GPS units. They all have flow meters. We're selling this to the farmers. They want to ensure that the material has been applied evenly across the field. Otherwise, they're not going to be able to value it the way they need to and the way we want them to. This is just an example of how we're trying to push the envelope on using the material as effectively and efficiently as possible. This is a picture of in-row, in-season application into corn. Basically, the corn is grown on 30-inch centers. The injectors are on 30-inch centers. The corn is planted with GPS. The application equipment is running on GPS, so it's automatically going down the row in between the corn rows. And this is using the material as efficiently as possible. This is a slide showing a 3-year study that we did with OMAFRA, which is the Ontario Ministry of Agricultural, Food and Rural Affairs, essentially Ontario's extension service, and Ontario Soil and Crop Improvement Association, which is a farmer-run organization looking at more innovative practices and how to maintain soil health. So again, this is not a Lystek study. This is a study that OMAFRA and the Soil and Crop Improvement Association did in order to verify that the material works. There's a lot of interest in the product, and so these groups had an interest in conducting the research. We worked with them, but it was their study. And essentially what the trial showed is that in wet years, because of the organic nature of the nitrogen, which can be released over time, oftentimes we get better results than commercial fertilizer. In 2016, there's a dry year, meaning there wouldn't be as much mineralization of that organic matter. The product worked as well as a commercial fertilizer. So this was done over 3 years. There was 12 different sites. There was 3 replications, 2 rates of Listergrow, 1 rate of commercial fertilizer, each replicated 3 times within each field. So very robust study. We got a lot of great information, and this is something that we use to promote our product, and we're happy to show some potential customers. So as a result of our efforts, we're sold out. We've sold everything that we produce, and at all of our facilities, our demand far outweighs our supply, even though our prices are increasing year over year. We've been running this program for about 4 years, and the word has gotten out, and farmers see the value, and they're willing to pay for it. So right now in Ontario, they're paying between $100 and $200 an acre for our material. And our customer list continues to grow throughout Ontario and California. So I've talked a bit about our fertilizer program. Because of some of the following presentations, I want to talk a little bit about the technology and how our technology can actually improve phosphorus recovery in wastewater treatment plants. So I'm going to introduce my colleague, Ajay Singh. He's our technical director.
Oh, hello everyone. I'll just take a few minutes actually to describe how Lystek material, Listergrow, which Mike just described, can be used in wastewater treatment plant, particularly in a BNR system to remove nitrogen and phosphorus, and also the phosphorus recovery. So Mike explained the Lystek process at mild temperature, 70 degrees Celsius, low pH and high shear mixing. That actually disintegrates biological cells. And not only that, it hydrolyzes and solubilizes complex organic molecules into simpler compounds. And that's where you produce high level of soluble COD in the final product of Listergrow. And it could be almost 40 to 50% of soluble COD of the total COD. And volatile fatty acids that actually can be used for carbon source in both phosphorus and nitrogen removal. And very high levels of volatile fatty acids are produced in the process. And you can expect in a Lystek product from 10,000 to 15,000 milligram per liter of volatile fatty acid. That includes acetic acid, propionic acid, and butyric acid. And these are readily biodegradable volatile acids that can actually help remove phosphorus and nitrogen from a BNR system. And as you know, that actually BNR processes require specific COD to nitrogen or COD to phosphorus ratios for denitrification and enhanced biological phosphorus removal in the system. And not only that, in anaerobic zone, when you add actually these volatile fatty acids as a carbon source from commercial sources such as methanol, glycerol, or acetate, you can actually, in the anaerobic zone, you release lots of phosphorus, and then in aerobic zone, the phosphate accumulating organisms, they accumulate phosphorus and take it out from the water phase, and the clean water goes out to the waterways. And these phosphorus accumulating organisms can retain up to 38% or more by weight of phosphorus in their body and cell body. So traditionally, actually, carbon-rich materials such as methanol, glycerol, acetic acids have been used, but they are expensive chemicals, and you can replace this Lystek product as a carbon source completely. And we have shown actually both in case of biological phosphorus removal as well as biological nitrogen removal. I'll give it back to Mike actually for further.
Okay, thanks, Ajay. So that wraps our presentation up, Matt.
Great, thanks a lot to both of you. I'll just ask you to go ahead and pass control over to Jeff Dawson. So all you have to do is unshare your screen, and Jeff, you can start sharing your screen. Meanwhile, I'll read a little introduction to Jeff. Again, please send questions via the chat feature that we can address at the end of the presentations. So Jeff Dawson is the CEO of Renewable Nutrients. And he has more than 20 years of experience in the investment and capital markets industry. As the CEO, he's responsible for overseeing the development and strategic planning of the company, including market exploration and opportunities for expansion. I should mention too that Renewable Nutrients is one of the organizations that sits on our board of directors, so we're very happy to have Jeff here. Jeff, you want to take it away?
Matt, thank you. Can you hear me okay, and can you see my presentation?
Both. I can hear
Perfect.
you and see you.
Great. I'm here to talk briefly about QuickWash, our phosphorus extraction and recovery technology. The technology was originally created by the USDA and licensed exclusively to Renewable Nutrients. It has applications both in the agricultural market and in the municipal market. In the municipal market, while there are a number of benefits, recovering more than 95% of the phosphorus available in a stream, reducing recycle loads, reducing polymer, reducing disposal costs, eliminating struvite scaling, and helping meet EPA nutrient requirements. Our mission at Renewable Nutrients really is to focus on the phosphorus issues inside of a facility. And while ultimately the benefit will be recovering and reusing the byproduct that we create, calcium phosphate byproduct, we could create a struvite product as well. But our goal is focused on the eliminating phosphorus issues that are inside of a municipal facility. We do that in a highly customizable technology that has two phases. The first phase is to solubilize the phosphorus out of any solids that we're treating. And once we solubilize those, we easily can extract those out into a byproduct. I'll get into the byproduct a little bit later, but it's important here to understand that this technology is agnostic in terms of equipment use, agnostic on scale, up, down, and primarily economically changeable based on size of a facility. And while every one of us in the market would certainly love to focus on 25 or 30 million gallon a day facilities and higher, and those facilities certainly become sustainable in terms of the amount of product they produce, there's a real issue and a real concern and a real market availability when you start talking about a more typical municipal facility, whether it's 5 million gallons a day or 1 million gallons a day. And because our technology is customizable, sometimes it doesn't make sense to recover. Sometimes it makes sense just to extract and solve the phosphorus problem internally inside of a system and eliminate the economics around the recovery and marketability of a byproduct. So each system we sort of deploy is customized that way, and we focused first on the needs of the customer and what they're trying to accomplish and where in their system they're trying to accomplish it. QuickWash can be configured in a number of ways, either on a side stream coming off of a dewatering, solid stream prior to dewatering, prior to thickening, can pre-treat industrial discharge, and also animal agricultural applications where we can treat manure directly. As an example, we're currently working with a large swine producer where we are extracting phosphorus in the form of calcium phosphate directly from swine manure out of lagoons, and we're testing that byproduct to be fed back to the pig. One of the most expensive ingredients in swine feed is the phosphorus component, and they're looking to sort of fill the loop on that system. Now, quick wash can be, again, because it's customizable, can be placed in a number of ways inside of a system. So this is a very simple diagram of where we would place quick wash if we're treating the solid streams directly. You would do this, obviously, if you're trying to land apply your solids and we're concerned about reducing phosphorus in those solids, as well as eliminating the phosphorus in the recycled centrate or filtrate stream going back to the headworks. If the biosolids aren't necessarily a concern in terms of land application, if those are disposed of in another way, then you wouldn't take the time or economics to treat those. You would just simply treat the centrate filtrate side that's being sent back to the headworks. You'd install quick wash, obviously, at that point to solve that problem. Quick wash is relatively a new technology. I guess we all are right now, but we've done a number of pilots, a number of trial locations. We're currently working on 3 installations in the Midwest right now. We've done pilots all over the country and at a number of facilities, both agricultural and municipal. Here's an example of a few that we've published some work from. I'll get into the data a little bit about what we do. Because the technology is so customizable, we can treat a number of different streams. We've done a lot of work on different municipalities and on different streams. But ultimately, we've had a high degree of success in terms of percentage extraction, both on a solid stream and on a liquid filtrate streams. You can see some data here that's on your screen. There are 2 points in our system that we measure. One is how much we actually extract. That's what we end up solubilizing. And then how much we recover of what we extract. And what we're seeing is numbers on the extraction side, typically in the 92 to 99%. And then ultimately on the recovery side, as high as non-detect left in the effluent stream going back to a headwork. Per se. The second stage is fairly simple in our process. And those stages are accomplished by pH moves and separations. So we have 2 separation points and we have 2 pH moves. And those pH moves are dependent upon the streams themselves and how much phosphorus actually needs to be extracted. And that's another part of the customized feature, is that you don't always have to bring the economics to extracting 90% or more. Sometimes we can solve the problem by extracting as little as 50% of the phosphorus inside of a stream. It just depends what the end user is trying to do. This is some of the facilities we've done some work at in the agricultural department. Since we're really talking about other issues today, I'll sort of briefly go over that. And then ultimately, I want to talk about our byproduct. Our byproduct is the calcium phosphate, and 99% of our P2O5 is recovered in calcium phosphate is plant available. It is in the form of an amorphous calcium phosphate, and it's more soluble than crystalline calcium phosphate. Our technology and our patent allows us actually to recover in the form of struvite if an end user desired, but we are focused on calcium phosphate primarily because of the economics involved and the fact that we can efficiently extract, recover the phosphorus in the form of calcium phosphate. We've done a lot of work on plant availability, and we've worked with the Department of Agriculture in the US, and we've done a number of studies. Some of those studies are published and available on our resources page on our website. But ultimately, our product falls sort of in between single and triple superphosphate in terms of what's available, and the availability is about the same as all of those. Our product really can be used directly, land applied directly, or it can be used as an ingredient for a more sophisticated product. For instance, a proposal we're working on now on the East Coast, they're actually going to provide the product to a fertilizer manufacturer who's going to buy it as an ingredient component. Because they're so close in terms of location to the facility, it's going to be an easy transport and use that way. This presentation is available obviously on our website, but one of the things I wanted to concentrate on is, again, going back to where we look at the issues ultimately with our technology, is that we're trying to make our technology as agnostic as we can, so we can focus on the needs of a facility and the end user, and we can customize those, the implications of and the disposition of the technology. So economically, it becomes viable even on the smaller side, on a 1 to 5 million gallon a day facility, where we're solving very, very specific phosphorus problems. In addition to creating a more complicated system where we can ultimately deploy on a larger facility and then create a high volume of byproduct that ultimately probably at the end of the day funds the system entirely. But the reality is you can't, or we don't view the opportunities in our market as one where we can let the tail sort of wag the dog. So with that, Matt, that's the end of my presentation. I'll hand it back over.
Great, Mike. Thanks so much for that. And while you're stopping your share, maybe Matt can pick up at the next slide. Thanks for the presentation, Jeff. Again, if you have questions for Jeff, please send them via chat, and I'll note them and we'll address them at the end of the speakers. I'll go ahead and introduce Matt Kuzma now. Matt is the Vice President of Nutrient Recovery Solutions at Ostara Nutrient Recovery Technologies. He has 25 years of experience in the global water wastewater industry, primarily focused on advanced technologies such as membrane filtration and membrane bioreactors applied for water reuse, nutrient recovery, anaerobic digestion with energy recovery, and advanced biological wastewater processes. His past experiences include work at US Filter, Veolia, Siemens Water Technologies, which is now Avaqua, Energia, Organica Water, and he recently rejoined Ostara to lead their efforts in implementation of nutrient recovery projects globally. Matt has a BS in engineering from Miami University, and he works with forward-thinking organizations to advance the cause of sustainability, including as a member of our board of directors. So again, it's nice to have another member presenting today. And thanks for coming today, Matt.
Sure, no problem. Hoping you can hear me okay. Just a bit of a sound check.
I can hear you just fine, thanks.
Okay, great.
And see your screen as well.
Great, perfect. So I'll apologize. I am getting over a bit of a cold, so you may hear me munching cough drops to avoid coughing in everyone's ear. But certainly appreciate you organizing this, Matt. It'd be helpful if one of us changed our name so we didn't get confused with the references to Matt, but that's okay. So I'm just going to talk a little bit about our success to date and kind of how we envision some of these things, and really look at the impacts of nutrient recovery, but also talk a little bit about the application of the recovered product and how that addresses the other side of the discussion. If we look at Ostara as an organization, I'll talk a little bit about company profile, what our solutions look like, and then we brand our fertilizer under the name of Crystal Green. So I'll talk a little bit about the fertilizer impact as well, because I think without talking about both sides of that coin, certainly at least half of the important message gets missed. So Ostara was founded on paper 2005. We implemented our first full-scale installation in 2008. So we've been around about 10 years now. Globally, we have, actually this is a bit outdated, we have 15 systems that's operational today, with an annual production capacity, greater than 20,000 tons per year. Within that, in the municipal space, population equivalent being fed into sites that utilize the technology is about 7 million people. So, quite often when we look at these sustainability metrics and phosphorus recovery as an overall objective, we look at it in terms of scale, how many people. Certainly when you get into the ag and other markets, you can look at animals as well. But on aggregate, across those sites, we have 50 years of Pearl operational experience. That's essentially the number of sites times the number of years operating at each site in aggregate. So, we have lots of experience. We've been proven as economically viable. And I think one of the key messages from our end is that we're doing this and we're doing this at scale. So I'll talk a little bit about one of our larger installations here in just a second. Not a lot of detail here in terms of how the process works, but functionally, it's an upflow fluidized bed reactor being fed one or two streams coming from the treatment plant. We have a pre-digested stream known as wash strip, and unfortunately, in the limited time here, I can't get into too many details on that. Certainly there's lots of literature and info out there, as well as quite often a post-digester dewatering stream. In the municipal space, of course, quite commonly we have to add magnesium to make up the third leg of our fertilizer product. Crystal green is struvite, chemically speaking. So magnesium ammonium phosphate, lots of ammonia typically available from the anaerobic digester, phosphorus being the ingredient we want to recover, and then magnesium being the third leg of the stool that we do often have to supplement. But with that, they get fed into the bottom. Effluent carries over the top. Top section essentially functions as a clarifier to settle out the particles. And then we have a recycle line to manage upflow velocities in the bed, allow us to separate the biosolids and other non-desirable particles that are in our feed stream to maintain the purity of the crystal green. And on a batch process, we pull product out of the bottom. I don't have any slides in here about the processing on site for the crystal green, but we do separate from the water and dry on site, which is also part of what allows us to produce a very pure product without pathogens, etc. The sites I mentioned in here, 15 municipal sites. We are working in the animal waste and the industrial side as well. Given this audience, I don't really delve into those details, but it is certainly very applicable to other market segments as well. If we look at the operational benefits on site, historical context was that most sites manage these phosphorus streams through chemical addition. Certainly recently, there's also been some technologies and methods that are looking at producing struvite, but they quite often sequester it into the biosolids. And so while that is a good mechanism for managing struvite-related issues within the treatment plant, sequestering into the biosolids doesn't allow you to improve the nitrogen-phosphorus ratios in the biosolids. It also essentially means you're hauling away that struvite at biosolids value, and it's not recovering it as a standalone fertilizer product that would offset conventionally mined fertilizer products. So there's lots of words on this, but essentially we look at this as a mechanism for producing a standalone fertilizer product while also mitigating the site operational issues. As I mentioned, 15 sites globally. Just looking at this visually in terms of the map, certainly you see a concentration in the upper Midwest, the East Coast, a couple of plants out west, and then 3 in Europe with another under construction in Poland. That'll be operational in somewhere around 14 months from now. So we are very active in Europe as well currently. One other site, I guess it's missing from here that is in design is in Atlanta as well. So we recently finalized a contract with the city of Atlanta. Just to give you a context for scale, the largest treatment plant in the Western Hemisphere would be the Stickney treatment plant in Chicago. This site went in operation about 18 months ago. So it's 3 Pearl 10Ks. We do make reactors of different sizes for different scale. Pearl 500, Pearl 2K, and Pearl 10K currently as standard products. And they've got the capacity on site to produce 700 or 7,500 tons per year. From their standpoint, this was all part of a larger objective that is starting to push into the upper Midwest, discharging into the Mississippi River to address the Gulf of Mexico hypoxic zones. So the district accepted a phosphorus limit, which it did not previously have from the Stickney plant. They implemented biological phosphorus removal with some modifications of their existing process. But the Pearl process really enabled them to do that without having the recycle come back from their dewatering operations. So through their analysis, they've identified a cost recovery specifically at 5 to 7 years. What they'll also say is the overall project, which included the biological modifications, as well as the Pearl installation and some other work on site, was in the range of $35 million. But when they looked at this in terms of life cycle, it was really, in the executive director of the district's word, the $35 million offset a life cycle cost of $700 million in terms of meeting their 20-year objectives for phosphorus limit being accepted. Switching over a little bit to Crystal Green, the fertilizer product. So one of the challenges, as we always look at this discussion in the municipal wastewater space, is the debate, the dialogue between the point source utilities and the non-point, meaning the ag community. And so I think one of the key messages here is that, and I'll show you some data here in a second, is that Crystal Green as a fertilizer product, due to its low solubility, also addresses the non-point runoff issues. We are registered as a fertilizer across the US and Canada, as well as Europe. As I mentioned previously, we've established a market for this product that has been a long effort. We do have a fertilizer team that develops all of the agronomic data and the fertilizer channel to market, which I think is important. So we're in many ways 2 companies in one, with a water technology market as well as a fertilizer market. And you'll see through this woven, we have lots of nutrient stewardship and other certifications that really go into demonstrating the success of the product. One of the key trials we did, as I mentioned, around the runoff issues is in the UK, some runoff trials done a couple years back. So what you'll see on the left-hand side is some measured runoff data. On the right-hand side would be time. And so at the top, the horizontal axis would be time. And you can see across this, the triple superphosphate is yellow, plus some existing available in the soil. Triple superphosphate alone in blue, and then the control in Crystal Green being in the green and the red at the bottom. And essentially what this shows is over a rainfall event, after having fertilizer applied, that the Crystal Green is not entering the watershed, it's staying in the soil and it's staying where the plants can access it. Whereas the highly soluble products end up moving into the watershed relatively rapidly. And so when we look at fertilizer applications, a big part of this is looking at the efficiency of use, meaning how much stays in the soil and how much is accessed by the plant, as opposed to requiring over application of fertilizer because much of it washes off into the watershed, which ends up causing lots of eutrophication challenges, of course. And all this has further been represented through some work being done in the Netherlands, where because of the large historical use of fertilizer within the Netherlands, which, as many probably know, punches well above their weight in terms of agronomic outputs in land size, but they also have lots of dairy and other operations, and so the conventional wisdom there was that the soils had been saturated with phosphorus. So we actually did a trial there with the Dutch ministry to look at what happens with use of crystal green in areas that have been banned for phosphorus application. And so within this, we actually showed significant yield increases. And within that, the discussion really becomes that not all phosphorus fertilizers are the same. And crystal green has been demonstrated through many of our trials to be what we call citrate soluble, where the phosphorus is released by the plant on an as-needed basis. So the roots excrete the acids that allow the fertilizer to access the plant to access the fertilizer on an as-needed basis, but it's not water soluble, so it will actually be retained in the soil even over multiple growing seasons. So with that, not all phosphates are the same. The other thing I would mention here around the fertilizer analysis is that all of the fertilizer we make across all of our sites is the same chemically. And that becomes very important in terms of giving a guaranteed analysis to fertilizer buyers so that it doesn't change seasonally, it doesn't change geographically, it doesn't change site by site. And so from that end, we have invested a lot of effort into managing that fertilizer distribution chain. I'll also mention that we have fertilizer purchase agreements with all of our clients. So in all of the markets, they're not required to take responsibility for managing quality control, certification, distribution, logistics, market development, warehousing through seasonal application. All of those fertilizer-related responsibilities fall to us, but yet we share revenue back with the sites. To make sure that they have a vested interest and see part of the value that's created through the fertilizer production. So in the bigger picture, we're of course looking to create a circular economy. The renewable phosphorus source, whether it's animal waste, industrial, or municipal wastewater, creating a fertilizer that can then be applied back to the land safely. Reducing the impact of additional fertilizer production, and then with that, kind of completing the circle for how that impact comes back into the food chain. So from us, it's certainly very much a story of creating the circular economy as it relates to recovering the phosphorus, using it back into the food chain. And so with that, a big part of this comes from a combination of benefits. In the wastewater applications, we're reducing phosphorus discharges, but at the same time, we're reducing the demand for phosphorus application and the associated runoff. And so it's really the combination of those two stories that create a much larger impact, especially as you look at getting into more and more production. It's really becomes a linear scale. And right now, looking into 10,000 plus tons of production across all our sites, that starts to be significant. And so from that end, just as a last summary, crystal green as our fertilizer product, Pearl as our nutrient recovery technology, And those two combined really tell a very strong story for how Ostara can be part of an organization such as this, driving these impacts at scale. And with that, I'm done. I know that you have questions towards the end, so I'll go on mute now. Matt?
Yeah, great. Thank you so much, Matt. That was very interesting to hear that presentation. And yes, we've gotten some questions on the line that we'll address at the end. But before that, we'll move on to the last presentation, which is going to be presented by Jordan Lin from CLEARAS Water. They have a different approach, one that's kind of near and dear to my heart as an algae biomass nerd myself. So I'll be interested in hearing what you have to say, Jordan. Just by way of introduction, Jordan is the CEO of CLEARAS Water. He has 15 years of senior level leadership experience in business development, sales and marketing, and strategic planning and operations management. Prior to joining CLEARAS, he oversaw business development for Alps Corporation, a nationwide financial and professional services firm. He's an active investor in early stage technology and service-based businesses. And he received both his BA and MBA from the University of Montana, the latter of which he graduated magna cum laude. Thanks again for joining us today, Jordan, and I'll let you take it away.
Thank you. Can you see my screen, and is sound check okay?
Yeah, both check out.
Okay, great. Thanks for having me. So CLEARAS Water Recovery was founded in 2008 with the onset of interest in alternative fuel sources, and in particular algae as an alternative fuel source as identified by the U.S. Department of Energy. And in that process, it quickly became clear that from a technical economic basis that algae-based fuels were an unlikely economic going concern, but that within the context of algae and what it requires from a photosynthetic activity process, the combination between what wastewater plants wanted to eliminate, being nutrients, carbon, and energy, algae was a natural process and mechanism because what the plants want to get rid of in terms of the wastewater facilities, the plants being the algae, require in terms of their biological activity. So the process that we've invented and that has now been patented and is scaling commercially is an advanced secondary and tertiary polishing technology for the recovery of phosphorus, nitrogen, and other contaminants. It uniquely, just make sure I can advance the screen here. Did you see that advance, Matt?
Yes, I did, Jordan.
Okay, so the technology itself is obviously complex below the surface, but on the surface, it's very simple. We have a mix phase, a recover phase, and a separate phase. And effectively, what we identified and found out was that eutrophication and these hypoxic zones, which are being proliferated by algae blooms, that being the problem allowed us to look at it and say, well, what if we were to take the problem and move it upstream into the treatment plant and control the algae bloom? So effectively, that's what we were doing, or that's what we do. We take the problem that is in these receiving body waters and we move it into the treatment plant, and then we control that environment. So the mixed stage combines typically secondary effluent with algae. That begins the treatment process. You end up with both a returns recycle stream of biomass and nutrient-rich wastewater, and you combine that with a carbon source. So at most of our facilities, and the large facility that we're currently commercially scaling in Salt Lake City, we're using waste carbon coming off of a food waste to energy digester, and you combine those three things in a mix well to really create this biodiverse mixture flow. That biodiverse mixture flow then transfers into a photobioreactor, which is essentially a plug flow reactor that is exposed to either sunlight or artificial light, and it's there that the photosynthetic activity really basically gets maximized, and nutrient recovery, including nitrogen and phosphorus, start to they get metabolized into the algae, and the ultimate impact is extremely high water quality. From the photobioreactor, we take the algae and the treated water, and we separate it using a level of submerged membranes. From that, you get basically three things. You get clean water, which is oxygenized. And when we talk about clean water, we're talking about phosphorus recovery down into the parts per billion levels. And there's a unique relationship in this environment where for every 1 part phosphorus that you recover, you also recover 8 parts nitrogen. So we're recovering both nitrogen and phosphorus, and that is the biological process that occurs regardless of whether you want it to happen or not. Ultimately, in most circumstances, phosphorus is the limiting factor, and therefore what we focus on, although there are some circumstances where customers are focused more on the nitrogen or ammonia levels, and we can kind of work the math of both ways from a biological and mechanical mass balance standpoint. So you get clean water, you get and you get a recycle stream. We call that the return activated algae stream. Off of that stream also comes an algal biomass. That algal biomass then is managed and sold into various markets, creating a residual and continual income stream for our customer and some component of cost recovery. This process that we've invented mimics traditional activated sludge plants, where you've got a waste activated sludge and a return activated sludge component, and you're essentially managing the waste rate of the mass in order to keep a food to mass ratio and relationship in line in order to achieve the nutrient recovery requirements that ultimately the plant that we're working at has to attain. From a system benefit standpoint, this is obviously a sustainable approach to nutrient recovery. Obviously, it's multi-constituent. We're working on both the phosphorus and the nitrogen. From a nitrogen standpoint, algae has an affinity to ammonia first, and then we'll begin to work on the nitrates. This process, the ABNR process, which stands for Advanced Biologic Nutrient Recovery, does not impact nitrites. The ancillary benefits associated with this, we remove obviously total suspended solids down to non-detect levels, significant reduction of biological oxygen demand. Carbon dioxide is recycled in this process. We hear a lot around sustainable technologies and the concept of carbon recovery. This is truly carbon recycling, no different than if you look out the window and see plant or grass. Those plants take in carbon and they give back oxygen. That's exactly what's happening in our process. So the concept of recycling carbon dioxide is a reality. And we increase the dissolved oxygen in the waste stream anywhere from 30 to 40%. This results in some pretty significant cost savings potentials for our customers. We work with them upstream to optimize their existing treatment plant. Most treatment plants, through their BNR process or night-D-night process, are working to get ammonia out of the system, when in reality we can somewhat detune what they're doing from an aeration perspective, which is one of the largest power and costs associated with running a wastewater plant. We can back off of the use of that because we're going to recover the ammonia anyway, and we're also going to discharge with an increased level of oxygen. So there's some optimization. Not only are they getting the benefit of the treatment capacity of our technology hitting their discharge requirements at the most stringent levels, but they're also realizing a fairly significant power savings upstream because we're going to recover the nitrogen species that they've attempted to put all this capital and operating costs into removing upstream of us. So That's a unique benefit. Obviously, this is non-chemical, so it eliminates any toxic sludge or no sludge handling costs. And it's very modular and scalable. It easily expands to meet both an increased flow requirement, but also you can basically retire the conversation of nutrients. Given the fact that we're achieving parts per billion on the phosphorus loading, and on a combination of that, you're achieving 8 parts of nitrogen recovery, you can use this as a single technology to address both of those constituents. From a performance level, just to give you kind of an example of where we see the results of this technology. This is a data set that included over 234 separate trials. Average phosphorus was 1.9 entering the mix well of our system, and the average treated phosphorus being discharged to river, lake, or stream or for reuse was 0.02 milligrams per liter. You can see a broad cross-section of various wastewater plants down on the horizontal axis, and then the concentration levels of the phosphorus on the vertical axis there. I would point out that, for example, at Avoca, as you'll see over here, and in some of these later commercial demonstration projects, the phosphorus loading was significantly higher as we were treating post-primary and sometimes advanced secondary versus just a true bolt-on technology to post-secondary treatment. So that's why you see higher loading on the far right of this versus on the left side of this. These plants, we're looking at it as a polishing technology. These plants are looking at it as a replacement for further investment in their secondary and advanced secondary processes. From a nitrogen perspective, to give you a sense, let's see, sorry, one second. Oh, yeah. So this is another example of the previous slide was a bunch of work that was done in the Midwest. This work has all been done in the state of Utah on this slide, but you're seeing very similar results. Phosphorus, regardless of kind of where the system accepts the loading, we are able to, through very detailed calculations and proprietary, I guess, algorithms, understand the food to mass relationship and the amount of time or contact time required between the algae and the effluent or the secondary effluent to achieve discharge level requirements. As I mentioned, the typical uptake between phosphorus and nitrogen, for every 1 milligram per liter of P, you'll get 8 nitrogen. This graph shows that relationship very, very well. That range can change. We've seen it anywhere from 6 to 20. So it's exciting when you think about the fact that you're not going to have to purchase multiple technologies to recover these constituents, and then you're putting them into a form of a biosolid that can be reused and sold into markets for cost recovery. To give you an example of the commercial success, we're currently in the construction of a $28 million project that was announced last year about this time. This is being constructed with, co-constructed with a food waste to energy project. Ultimately, they were faced with the decision of whether to create an entirely new BNR plant or to upgrade their, or to bolt on to their existing trickling filter infrastructure. The big pressure on the plant was the fact that the food waste to energy project was going to put additional pressure on nutrient removal of the existing plant. So CLEARAS was chosen as the technology of choice, allowed us to extend the life of that existing asset, was significantly more cost competitive on a CapEx basis, and then significantly more cost effective on the life cycle analysis. This is a 4 MGD plant, reducing phosphorus from 3 milligrams per liter to less than 0.035 milligrams per liter. We will recycle about 17,500 pounds of carbon dioxide a day and generate 8,000 pounds of algal biomass daily. 100% of that biomass has been sold for plastics and foams, and the customer receives a residual income stream for the sale of that, similar to the Ostara folks. Excuse me. We take the responsibility for effectively the monetization of the biomass agreements. We do the marketing, we do the sale, we do the contracting, we do the APAR, we do logistics management, we do quality control, quality assurance. All of those things happen through our subsidiary company called CLEARAS Bioresources. And again, it's very exciting because 100% of this biomass has been sold for sustainable plastics and foams. Those foams and plastics are going into the shoe market, in which this single customer has an annual demand of 22,500 tons. And this plant at 8,000 pounds is going to produce about 1,500 tons a year. So very excited about the potential of that, and from an overall perspective of circular economy, really making that happen. Here is just a plant diagram of how the system is going to be laid out. If you can look in the bottom left corner, this is your mix well. Up above, you have the plug flow photobioreactor systems where the biologic activity is really maximized. And then down here, you've got a separation phase. This piece of the plant is already constructed. We already have this up and running. It's 1/80th of the size of the full plant. It was done to optimize performance and characterize the biomass for offtake agreements or sale agreements. So we were effective in implementing that 1/80th design, which will just be duplicated 80 times here to mitigate risk for the customer relative to the biomass offtake and water quality produced. From a co-product opportunity standpoint, this, as you can see, produces a fairly large amount of biomass. That biomass then is qualified and characterized to determine the consistency and normalization of the product based on feed stream inputs, what the feed stream contaminants could be or potentially be, the quantity of biomass that we will produce, and then overall quality and characterization. Finally, these are the major markets that we are working in. The 5 major markets are soil amendments, food and feed, bioplastics, biofuels, and biochemicals. Not from a fuels perspective in terms of as you might think about it from a Department of Energy perspective, but specialty fuels and derivative products that come from the fuels process are certainly something that we're engaged in. We're also engaged in the creation of a hydrolyzed protein that can be placed into the human food market, in addition to the bioplastics and foam space. So very exciting growth potential and opportunities in that space. And then just to give you kind of an overall summary of the CLEARAS advantage over kind of what would be the chemical alternative standard. Obviously, we're chemical free. We produce this valuable co-product. We provide a comprehensive solution, meaning multi-constituent recovery over alternatives, and we can achieve current and planned effluent nutrient water quality requirements. On the chemical side, obviously it's chemical intense. You have toxic waste to deal with. You basically just transferred the problem from a liquid to a solid state, only solving a singular problem. And then those technologies struggle to meet existing and planned effluent nutrient water quality requirements. So overall performance, sustainability, scalability of the solution, and co-product value result in what is a lower total cost of ownership to customers over the competing technologies. With that, I'll end, and thank you for your time and the opportunity to participate.
Great, thanks so much, Jordan, for that presentation. Algae certainly are interesting and versatile little biofactories, and it's pretty cool what you guys are producing there. I'm going to go ahead and start the questions and answers session. And so again, if you could stay muted, we'll just go ahead and take the questions via the chat feature, and I'm going to post them up here on this next slide so everyone can see what the questions are. So the first question that was posed, I think was for you, Mike Dougherty. And it was, how are you regulated as a fertilizer in Canada and as a biosolid in the United States?
That's just a difference in the regulations between Canada and the United States. In Canada, the Canadian Food Inspection Agency allows for registration of fertilizers that are biosolid based. In the United States, if it's a biosolid, at one point it will always be a biosolid. So it's just a difference in the regulations.
Got it. There was a second question here for you as well, which is, do you somehow remove or eliminate the microparticles that are in the sludge? And there's a reference to a Danish study about microplastics in sludge. Microparticles, no. I'm sorry, not, it could be microplastics, but the question's microparticles.
No, we manage the biosolids as they are. We rely on the science that looks at the ESOX or other materials and the safety of applying the material, but no, we're not removing.
Okay. So the next question we have for Jeff Dawson. Where do you see the market for extraction and recovery in the short and long term, Jeff, for phosphorus extraction and recovery, that is?
Well, I think, you know, in terms of the market and where we stand, we're sort of at the front door of this. But ultimately, long term, as we look at this, there are two fundamental issues, right? The economics of it, can it be done at some reasonable cost? And then, are you solving a problem? You can't sort of solve half the problem. You have to have a technology that eliminates a facility's issues around phosphorus and then provides secondarily benefits to that issue. A good example of that is we're working with a very large facility that has currently a struvite extraction recovery technology in place, and they're looking at our technology to actually go behind that to recover the phosphorus that's coming off of that technology and the effluent stream being discharged. So again, there's ultimately the facility has to have some sort of technology that solves the problems they're facing and done in an economic way. So I think what we'll see over the market over the next 5 years is, the cost of these technologies will continue to go down. And then the focus will be on the issues on a facility, and then secondarily the byproduct, I think, providing value to that facility or facilities.
Yeah, and I wonder, have you maybe penciled this out at all? One of the problems with trying to valorize these byproducts is that phosphorus is really cheap, right? Phosphate rock trades at a very low price. Have you ever thought about or figured out how much change there would have to be in the price of phosphorus before that byproduct becomes valuable enough to be its own argument for phosphorus recovery without?
There are a couple of components to that, not just pure price, right, but volume. So, for instance, if you're looking at recovering phosphorus from a large-scale facility, 20 million, 60 million gallon a day facility, you're going to create enough volume of product that there's going to be value there. If you're extracting phosphorus from a 1 million gallon a day facility, you're just never going to have enough product to make that, marketable for the cost of extraction. So, at some point, I guess in theory, if the price of phosphorus goes up and it goes up enough, then the break-even facility size of 20 million may go to 15, may go to 10. But ultimately, as we're all looking at these long-term availability charts of 80 or 150 years of mineable phosphorus, ultimately we're going to get to that, where we're going to have to be on more of a recovery standpoint. And you're looking at states now. I mean, Vermont's pretty interesting in what they're trying to do is end all importing of phosphorus, right? So that means you're going to have to recycle everything inside that state. So there, just depends on one, not just the financial value of the phosphorus, but also on how tight regulators are going to get and how the regulation of this plays out.
Great, thanks. We had another question. This one was directed to Matt Kuzma. And it was that in Europe, there's recently been some media about struvite and the risk of adding antibiotic-resistant genes to the environment. And this questioner wanted to ask if you had any comment on that.
Sure. Well, I think this is a bit misleading in terms of the context of the report and the data that this was based on. This study, and I don't know if they were referring to the same project, but specifically the study that we've seen was done on struvite extracted from swine waste in China. And if you look at that, the real challenge that they haven't identified, first of all, the product they used wasn't pure struvite. It was mixed in with some additional solids, most likely which came from the swine waste. But the secondary part of that is that swine waste has an order of magnitude higher antibiotic content to it relative to biosolids, as an example. So the use of antibiotics in animal operations is significantly higher than the broader human population. So there's a few related challenges there, both in terms of the source material, but then also the purity of the product. And so this is something that we have collected some data and looked at. But the reality is that right now, if you look at common agricultural practices across North America as well as the world, is that swine manure is being used for fertilizer already. And so the struvite that is captured from that would have significantly less content than manure. So it's a much broader, I think, study and a broader analysis. We have to differentiate feedstocks as well as competitive alternatives and continue to collect some data. But our initial data shows that struvite recovered from the operations we've seen in the process that we use, which is not the same as everybody else, is going to be significantly cleaner than any of these analyses have shown.
Sure. Well, thanks for that. I think that was the last question that came through. And we're getting close to time, so maybe we should just wrap up. Although, if any of you has a question for any of the other presenters, so if there's inter-presenter discourse, I'd like to give some opportunity for that. So do any of the presenters want to ask any of the other presenters questions, or should we just wrap up? No one? Okay, no takers. So we'll go ahead and wrap up today's session. I appreciate all the time that the speakers put into preparing presentations and working with me on this. And I thank you all for coming out to this Sustainable Phosphorus Series webinar. We do these quarterly, with the off quarter being the one time when we have our actual live phosphorus forum. So we'll be doing another one of these in about 3 months, and I hope you'll look out for the announcements for that. Thanks again, and I hope you all have a good day.